Step off a blindingly bright sidewalk on a 95-degree July afternoon, walk through double glass doors, and you're suddenly standing in a crisp 68-degree oasis. It is natural to assume the rattling box in the window is functioning like a winter generator, actively churning out cold air from nothing. In reality, air conditioning is a thermal heist. The machine steals existing heat from inside the room, captures it, and forcefully dumps it outside. We rely on this continuous heat theft so heavily that it dictates the shape, height, and density of almost every modern city on Earth. Keeping those indoor spaces comfortable requires enormous power. Heating, ventilation, and air conditioning systems account for nearly 40% of a building's energy use. Because these systems consume nearly half of a skyscraper's power, inefficient mechanical design turns a modern building into an invisible energy vampire, draining the local grid. This animation shows a closed-loop pipe system, demonstrating the single rule of physics that makes mechanical cooling possible: phase change. This is the scientific principle where a liquid absorbs a massive amount of heat energy from its surroundings as it boils and turns into gas. The liquid is forced through a tiny nozzle. This instantly drops the pressure, turning the refrigerant icy cold again, ready to reset the loop. That relentless four-step mechanical heartbeat, evaporator, compressor, condenser, expansion valve, is the exact same sequence humming inside every bedroom window unit. Left alone, heat always flows from warm areas to cold ones. The vapor compression cycle uses brute force mechanics to force thermal energy to flow in reverse. But you cannot hang 10,000 window units on the side of a modern glass high-rise. The sheer volume of internal air trapped inside these towers requires a completely different scale of engineering. Large commercial spaces rely on an air handling unit, or AHU. You can think of this massive piece of machinery as the central respiratory system, the lungs of the entire building. It starts at the mixing box. The AHU pulls in stale return air from the hallways and offices, blending it with fresh air from outside. This precise mix guarantees the oxygen levels stay high enough that occupants do not become lethargic from carbon dioxide buildup. Instead of pumping volatile chemical refrigerants through 50 floors of ductwork, these enormous systems typically pass the air over coils filled with chilled water, supplied by a heavy-duty central plant in the basement. Finally, massive supply fans physically push that newly chilled, filtered air through miles of hidden sheet metal ductwork to reach people working deep in the building's interior. The AHU takes a localized trick of physics and scales it into an automated respiratory system, capable of keeping thousands of people alert inside sealed boxes of glass and steel. Simply running enormous fans and pumping 50-degree air into a skyscraper blindly results in freezing rooms, inconsistent humidity, and thousands of dollars of wasted electricity. To manage this, modern architecture relies on a building management system, or BMS. The BMS is a centralized digital brain that actively monitors and adjusts temperature, humidity, and airflow across the entire property. This diagram illustrates a variable air volume, or VAV box. Rather than running at full blast all day, sensors detect when a conference room is empty, and the BMS simply closes a physical damper inside the duct, blocking airflow to that specific zone to conserve power. The system regulates the water valves using PID loops. A PID loop is a continuous mathematical calculation that measures the difference between your desired temperature set point and the actual room temperature, allowing the system to gently adjust the cooling output without overshooting the target. And when the outside temperature drops to a crisp 55 degrees, the BMS activates economizer mode. It completely shuts down the energy-heavy mechanical chillers, opens the exterior vents, and uses the naturally cool outdoor weather to provide free air conditioning. These digital control loops and sensor networks, reining in the brute force thermodynamics at the chiller plant, turning a raw industrial process into a precise, on-demand utility. Every cool breeze is the culmination of a highly choreographed sequence, a precise dance of boiling liquids, chilled water, and automated dampers working in unison. With commercial real estate consuming such immense amounts of electricity, rigorous mechanical design and smart control logic are the only things standing between sustainable urban infrastructure and an overloaded power grid. The next time you hear a vent kick on above your desk, try to look past the illusion of cold air. You are sitting at the end point of a high-speed, mathematically calculated game of thermal tag. We have engineered the ability to catch heat, compress it, and force it out of our buildings, securing human comfort in environments that would otherwise be uninhabitable.